Have you ever wondered how Linux ensures security and stability while running millions of lines of code? The answer lies in the concept of user mode and kernel mode. These modes keep your system secure and stable. Welcome to System Programming Series. In this video, we will explain what these modes are, why they are important, and how they work together. If you want to master system programming, subscribe and level up your knowledge. Let's get started. So, why do we need modes? And what is the risk if we don't have different modes? Let's say we have different applications running on the system, and these applications are trying to access the system memory and hardware resources. First application tries to access the memory and hardware resources. Second application tries to access the similar memory and hardware resource. And third application also tries to access the portion of similar memory and hardware resources. So in such case, right, if all programs could directly access hardware or modify system critical data, the result will be chaos. And moreover, a single buggy program could crash your entire system. Or worse, a malicious software could gain full control. This is why we need controlled access, which is where user mode and kernel mode comes in. What are user mode and kernel mode? User mode is where regular applications run. It has limited privileges and cannot directly access hardware. Kernel mode is reserved for operating system. It has full access to hardware and system resources. User mode has restricted access and operates in safe sandbox environment. Kernel mode has full control over hardware and manages system resources. So what happens in user mode? In user mode, applications run with limited privileges. They cannot directly access the hardware or critical system memory. User mode ensures that applications operate within a safe sandbox. Even if one application crashes, it won't affect the other system. In user mode, applications run in isolation. They cannot access hardware directly, and crashes are contained to this specific application. What happens in kernel mode? A kernel mode is where operating system kernel operates. It has the authority to manage hardware. It manages process, schedule tasks, handle memory management. But this power comes with the risk. A bug in kernel can bring down the entire system. In kernel mode, kernel has full control of hardware, manages critical system resources like CPU, memory, and devices, and bug in the kernel mode can crash the entire system. Now let's understand how these modes interact. Most of the program needs kernel level services to perform tasks like file operation, network communication, etc. This requires a mode switch. A program requests a service using system call to transition from user mode to kernel mode. System call acts as a bridge between user mode and kernel mode. Hardware interrupts or software exceptions also cause transition to kernel mode. Application in user mode requests a resource via system call. When a system call is made, CPU switches from user mode to kernel mode. Kernel recognizes the system call, executes the needed operation via system call, and prepares the return values to return to the user mode. And execution context is returned to the user mode. And then application resumes execution. Application in user mode requests a resource via system call, then mode switch happens. Kernel performs the operation and returns control to user mode. Now let's develop a program to write to a file and let's understand how call switch happens from user mode to kernel mode with the help of example. Now let's understand the use of system call with the help of this example. Here this code opens a file using fopen library call, declares a constant string and writes the string to file using fwrite library call, and once write is successful it closes the file using fclose library call. Let's compile this code and run. Here as you see it creates an example.txt file and it writes hello system calls to this file. Where does the system call come into picture? Let's understand with the help of stress tool. Let's run stress on an executable file. We will create a separate detailed video on how to use stress to debug complex applications. For now, understand as Stress is a Linux tool that traces the system calls and signals made by the program during execution. It provides a detailed log of interaction with the kernel. Let's run the stress. As you see here, stress gives the entire call log. Here, when fopen is called, the corresponding open at system call is called. For the fwrite library call, corresponding write system call is called. And for fclose library call, corresponding close system call is called. In this case, in user mode, fopen, fwrite, and fclose prepare the operations and manages buffers. Control temporary switches to kernel mode through system calls, open at, write, and close. After completing each system call, control returns to the user mode to continue program execution. To summarize, here are the key differences between user mode and kernel mode. User mode has restricted access to hardware, whereas kernel mode has full access to hardware. User mode runs in low privilege level, while kernel mode runs in high privilege level. In user mode, if one application crashes, it affects only that application. But if kernel crashes, it affects the entire system. To transition, user mode uses system calls to access kernel services, while kernel mode operates directly on system resources. User mode has limited access to memory. Access is only limited to process's own memory, while in kernel mode, kernel has full access to the system memory. To recap, user mode is designed for safety and stability, while kernel mode provides the power to manage hardware and system operations. This separation ensures security, stability, and efficiency in Linux system. Now you know the key differences between user mode and kernel mode. In the next video, we will dive deeper into system calls, the bridge between these two modes. Stay tuned and don't forget to subscribe to continue your journey into system programming. Thank you very much.